All right, let's talk about something that's a real headache for developers in concurrent programming, the race condition. It's the silent, sneaky kind of bug that can mess up your data and make your apps act completely nuts. Seriously, figuring this stuff out is a huge deal, not just for writing solid code, but it's also a classic question you'll get in tech interviews. So by the end of this, you're going to have a crystal clear idea of what a race condition is, why it's happening, and most importantly, how to stop it.
So here's our game plan. We'll start with two basic ideas that are great on their own. Then we'll see how they can mix together to create a real mess, leading to a super unpredictable bug that we'll actually see in some code. Once we figure out what's going on, we'll look at the standard Java fix for it. And then we'll wrap it all up with the key things you need to remember whether you're coding or getting ready for an exam. Okay, before we even look at a single line of code, let's think about a real-world problem that nails this concept perfectly. Imagine you and your friend share a bank account. Let's say there's $1,000 in it. Now, at the exact same second, you both go to different ATMs and try to pull out $700. The bank's computer checks the balance for you, sees $1,000, and says, "Yep, approved." At the same time, it checks for your friend, sees that same initial $1,000, and says, "Approved" for them too. So, what happens? Did the bank just lose $400? This exact scenario is what we're about to see happen in software. To really get our heads around how a race condition happens, we first need to look at the two main ingredients. By themselves, they are fantastic tools for any programmer. But when they start interacting without any rules, well, that's when they create the very problem we're here to solve. These two ingredients are threads and what we call shared mutable state. So on one hand, you've got threads. These are amazing. They let our programs do multiple things at once, which is why our apps feel so fast and don't freeze up. Think about a web server juggling requests from tons of users all at once. Then, on the other hand, you have mutation, or shared mutable state. It's just a fancy way of saying we have some data, a variable sitting in memory that can be seen and, more importantly, changed by all those different threads. Both of these are absolutely essential for building complex software. So, we've got our powerful concepts, threads and mutation. But this is where our story takes a sharp turn. Let's see what happens when these two collide. And here it is. This is the million-dollar question for this whole explainer. What happens when all these fast parallel threads try to read and then change the exact same variable at the exact same time? This is our ATM problem, but in code. And this is where everything starts to go wrong. Okay, enough theory. Let's jump into some really simple code. This example is going to show the bug in action, and trust me, the results are pretty eye-opening. Our setup is super simple. We have a counter object. It has one variable inside, an integer called count. Then we spin up two separate threads, and each thread has a simple job. Call the increment method 10,000 times. And that method just does one thing, count plus plus. So logically, what should the final number be? The math seems obvious, right? Thread 1 adds 10,000. Thread 2 adds another 10,000. The final result has to be 20,000. No brainer. But when we actually run this code, we get a weird result, like 17,842. And what's even crazier, if we run it again, we might get 19,211, or maybe 16,500. It's a different, incorrect number almost every single time. We're literally losing updates. What on earth is going on here? To solve this mystery, we have to pull back the curtain and see what the computer is actually doing. It turns out our simple assumption about how count plus plus works is just plain wrong. Now this right here is the absolute heart of the problem. As programmers, we look at count plus plus and we see one single, unbreakable action. In computer science, we'd call it unbreakable operation atomic. But the big reveal, the crucial insight is that count plus plus is not atomic at all. See, under the hood, even something that simple is actually a sequence of 3 different steps. First, the CPU has to go read the current value of count from memory. Second, it adds 1 to that value. And third, it has to write that new value back into memory. The problem, the entire problem, is that the operating system can pause a thread and switch to another one right in the middle of these steps. And this table just perfectly illustrates the disaster. Let's say count is 3. Thread 1 starts step 1, it fetches the value 3. But whoops, before it can do anything else, the OS pauses it and lets thread 2 have a turn. So thread 2 times also fetches the value of count, which is still 3. Now they're both working with old data. Eventually, thread 1 wakes up, calculates 4, and writes it back. Then thread 2 does the exact same thing. It also calculates 4 from its old data and writes it back. We called the method twice, but the count only went up by 1. That's a lost update. That's the race. And that, my friends, is the official definition of a race condition. It's a bug where the final result depends entirely on the random, unpredictable timing of when the threads get to run. It's this randomness that makes these bugs so incredibly frustrating to find and fix. So, how do we fix this chaos? How do we bring some order back to our program? Well, the answer is we have to force the threads to take turns. We need to make sure that this critical piece of our code can only be run by one thread at a time. We need to make it thread safe. In Java, the fix is actually shockingly simple. We just add one single keyword to our method, synchronized. That's it. By doing this, we're basically putting a lock on the method. When thread 1 wants to run it, it grabs the lock. If thread 2 shows up while thread 1 is inside, it gets blocked. It literally has to stand outside and wait until thread 1 is done and releases the lock. And with that one tiny change, we run our code again. The result? 20,000. And more importantly, it is 20,000 every single time. We've gotten rid of the race. Our program is now predictable and correct. So what we've just done is we've made our code thread safe. This is a huge goal in concurrent programming. It just means our code is now tough enough to handle being hit by multiple threads at once, without breaking, without corrupting data, and without giving us wrong answers. Okay, we've gone through a lot. So let's quickly recap the most important things from this lesson that you'll want to remember. Just remember this flow. The recipe for a race condition is simple. Multiple threads trying to change one shared thing. The root cause is that simple-looking operations like count plus plus are actually multiple steps. The symptom you'll see is totally unpredictable and wrong results, and the solution is to control access using something like the synchronized keyword, which makes your code thread safe. And I'll leave you with this to think about. A simple counter is a great example, but this problem can be hiding anywhere you have data that's shared and being changed. Think about a settings object, a user shopping cart, or some data cache. Keep an eye out for this pattern, and you'll start writing way more solid, reliable code. Now that you know what you're looking for, you can start hunting down these silent bugs.